My Thermal Mug Project, presented by Team Purple, Calvin Connor, Mark Garber, Darren Mabe, and Vince Schwartz. Our goal for this project was to design a mug that has the ability to change the temperature of a beverage from room temperature to nearly 32 degrees Fahrenheit.
The reason we decided to take on this project was that other products in the market that attempt to do the same thing perform poorly. They don't cool a beverage nearly enough. We believe that the customer base for a project like this would be very large. Anyone with a fridge that likes their drinks cold could potentially be interested in our design. It performs vastly better than the competition and is only slightly more expensive. It also aligns with the two drivers, the driver of acquiring, because it's a simple tech product that's also somewhat of a fun novelty item, and also the driver of safety and convenience by increasing comfort.
Learning experiment design is beneficial to all engineers to produce an accurate working design. There are good habits that can be built as a student because you can apply these methods to all learning experiences. In addition to helping you as a student, learning these methods will make working with you easier for colleagues and will give companies a solid understanding of your intent.
The goal of the glass mug experiment was to understand what the specific heat capacities of a material means. To do this, we took a frozen glass mug with a relatively low specific heat and added warm water, which has a very high specific heat capacity, and recorded what the equilibrium temperature was. With this experiment, the temperature of equilibrium was always much closer to the temperature of the water than the temperature of the mug, because the amount of energy it takes to raise a given mass of glass 1 degree is much lower than the amount of energy required to decrease the temperature of the glass by 1 degree. This can also be explained as the water has a much higher heat capacity than the glass. For our ice melting experiment, the goal was to better understand latent heat energy of fusion. We did this by exploring how much heat is required to melt ice. The simplest way that we found of doing this was to take a measured amount of water at a specific temperature and a measured amount of ice at a specific temperature, combine them in an insulated container, and measure the temperature of the water after the ice had completely melted. When using the specific heat capacity of both materials to calculate what the final temperature should have been, the actual temperature was always lower. This difference in temperature is called the latent heating energy. Latent heating energy is the amount of energy required to cause the fusion of a material without temperature change. Latent heating energy is caused by the atomic bonds that form the material. Water has an extremely high heat capacity and latent energy because of the extremely strong hydrogen bonds that form it. So when combining equal weights of water and ice, the final temperature will always be lower than the average of the two because some of the energy of water used to melt the ice rather than raise its temperature.
The Arduino is hooked up to the LCD and temperature sensor. An input voltage from the temperature sensor is converted to degrees Fahrenheit by the Arduino and sent to the LCD once every second. Although the waterproof temperature sensor is not shown in this configuration to keep the picture simpler, it plugs into the same place as the current temperature sensor.
To waterproof our temperature sensor, we splice the sensor into wires. We then shrink wrap the wires to cover the exposed splice. Each wire was shrink wrapped individually and once bound together. To finish the waterproofing, we sprayed the shrink wrap and sensor with a rubberized paint that is both durable and waterproof. We used a spray paint to make it easier to provide a thin, even coat to reduce air in the sensor after the waterproofing process. Our mug design consists of an outside layer of ceramics, including a hinge top similar to that of a beer stein to insulate the system, and an inner thin layer of copper to provide a good heat conductance between the beverage and the mug core. The mug core is made of ammonia, which will not freeze in any standard freezer, but has a specific heat greater than water. Performance-wise, if our mug weighs 2 pounds, that mostly being ammonia, and we pour 16 ounces of room temperature water into the frozen mug, our final temperature will reach -7 degrees Celsius, which should remain for considerable time in the insulated mug.
Time was one of the biggest challenges that we faced, and most of our strengths involved overcoming this challenge. Individually, we practiced good time management, and as a result of this, we all came prepared to group meetings and were able to work efficiently as a group on the project to get killer results. Furthermore, We assign tasks according to our strengths so that we achieve stellar performance in an efficient manner. Many of our weaknesses on the MUG project also stemmed from time. Due to our conflicting schedules, we were only able to organize 2 group meetings. We also put off soldering the LCD until the weekend and had to buy a soldering iron since the labs were closed. Because of our difficult schedules, much of the project was done individually and we later combined our results. From this project, we learned how to use specific heat to calculate the equilibrium temperature of a closed system using the law of conservation of energy. We also learned as a group how to work efficiently with limited time by being focused and goal-oriented. Part of this process included using a diamond to quickly brainstorm many different ideas for the MUG design. By applying what we learned on the bike lift project, we were able to produce quality results with limited time, and by learning from this project, we will be able to produce even more awesome projects in the future.